And welcome to yet another lecture. This lecture is on generative adversarial networks. If you remember from a few weeks ago, we covered adversarial inputs, that is the types of inputs they may fool a classifier into mislabeling them. And one solution to the problem was that we can use the adversarial inputs to our benefit by using such inputs at the training stage, where we can generate our some adversarial inputs from the original inputs, and then we can combine them, we can augment our original training set with those inputs, and in that the network that would be created after training through these the combination of original inputs and adversarial inputs to be a more robust classifier, and that can deal with adversarial inputs as well. So to produce such adversarial inputs, we use generative adversarial networks. They are called generative adversarial networks because they are generative in nature. They generate the inputs instead of producing outputs from some inputs. It produces the new inputs based on some inputs or based on some distribution which looks like the original inputs, which is of for example of the same dimensions, or include similar objects as the original inputs. That's why they are called generative adversarial networks. These networks are not always used to create adversarial inputs or for adversarial purposes, but because of their main reason or the main objective behind these networks, they are the term that is used to describe them, or the nomenclature is still generative adversarial networks, or GANs. So here in this image you can see, in these images you can see some examples where there are images which can be mislabeled or which are adversarial in nature and produced through generative adversarial networks. These images are generated through a network which is called Big GAN, which can be found in a paper at this link. So let's begin our lecture. Okay, just give me a minute. See what these gains are. Okay, so here is a brief outline of the topics that we will be covering in this lecture. We would start with the different tasks of generations. Original gain formulation, then there are two variations on the gain formulation. There are NS gain and DC gain. Some other popular formulations or more recent ones, which are W gain and W gain GP and LS gain. And then we'll discuss the methods to evaluate gains and state of the art architectures. Okay, so let's look at some generative tasks that we can perform through generative adversarial networks. The first type of task is called generation, which is to learn to sample from the distribution represented by the training set, and it's an unsupervised learning task. So in this type of generation, we do not use any labels while producing adversarial images or adversarial inputs. That is, we learn the distribution of the data in the training set and use that distribution to produce new images or new inputs. So that is an unsupervised learning task. Another type of task is when generation is conditioned on class label. That is, at the input we have some original inputs and their corresponding labels, and based on them we produce some more synthetic images or synthetic inputs. That is another type of generative task where the generation is conditioned on class labels. For example, there are different inputs of the same label, goldfish, and we can produce more inputs corresponding to the same labels, but which are different than the original inputs, but with the same label. Okay, so here is some more examples of generative tasks where the generation is conditions on image. So we are not using the distribution of the image of the inputs or the labels of the images, but the images themselves. So in other words, you can call them as image to image translation. So for example, at the input, if we have a label like this, a segmented image with the segments are colored based on their labels and converting them into another image which is an actual scene. So this type of task is called label to street scene. There are some more examples: label to facade, black and white to color, an aerial image to an output map, and so on. So we can perform many. There are many different types of real life tasks that can be performed through generative adversarial networks, where the generation is conditions on image. So at the input we have an image, and at the output we have another image, which is somehow a representative of the same image as at the input, but in a different form, or in a different formation. So let's see how we can design a network for these generative tasks. So we need an architecture that can generate an image. So for any type of generative task, we need an architecture where the output is an image. So whether it's an unsupervised task, whether it's image-to-image translation, or a label-based image generation, in all of them at the output we need an image. So for example, in the first case, if we have an unconditional generation, then at the input we have a random seed or latent code, some output from a previous of a previous architecture, and we convert them into an output, a feature map of the same dimensions as the image that we need, through, for example, upsampling or deconvolutional or unpooling. If we condition it on an input image, then it becomes an image to image translation. So if we use the full architecture of the dense prediction, then we can use it for image to image translation. We can use the upsampling architecture for the dense prediction. So we have a downsampling, then an upsampling to produce an output which is of the same dimensions at the input, but different than the input, but representing some form or some representation of the input. So we have at the input we have a real image, and the output we have a synthetic image. So for that we need to design the right loss function and a training framework. So now we know we can use a certain input, which could be noise or a random seed or another image, and train a network to produce an output which should be in a synthetic image. So for that we need to design the right loss function and a training framework. So that is, we need to learn to sample. So for example, if we have some training data X with a distribution represented by P data, and we need to generate some samples X with a distribution represented by P model, and then we want this P model to be as close to as P data. So if these two matches, we will produce samples generated from the same distribution as the inputs. So let's see how generative adversarial networks can be created based on these concepts. We can train two networks with opposing objectives. The first network is called a generator, which learns to generate samples, where at the input we have a random noise or a random seed, and a generator is used to produce a synthetic image, and then we have a discriminator, another network, which learns to distinguish between the generated and real samples, or a fake sample and a real sample. So for example, if to the discriminator, if this input is given, it will detect it as fake, while if an original image is given, it will detect it as real. So if we can train two of these networks, both of these networks, G and D, where the G is the generator and D is the discriminator, together we would create a generative adversarial network. So let's see what the objective function is, which we want to optimize for the GX and DX to work. So the discriminator should output the probability that the sample X is real. So the discriminator is basically a binary classifier. So at the output we have the probability that the input is real. So if that probability is, for example, if it's below 0.5, the input would be detected as fake. If it's above 0.5, the input would be detected as real. And we want the dx to be close to 1 for real data and close to 0 for fake, or less than 0.5 for fake. And then for this task, the expected conditional log likelihood for real and generated data is given by the expected log likelihood of dx, where x is the distribution of x is represented by p data, plus the expected log likelihood of 1 minus dx, where the x is produced by the distribution of the generator, or ex belongs to p data log of dx plus ez belongs to p log of 1 minus dgz. So since now dx is equal to dgz and where z is the input to the generator and gz is the fake output or the synthetic image, and the z now belongs to for example, a normal distribution or some simple distribution like normal distribution or uniform distribution. So this is the overall objective now, which is a function of generator and discriminator model, that is expected log likelihood of dx plus the expected log likelihood of 1 minus dx or 1 minus dgz. The discriminator wants to correctly distinguish real and fake samples. So a good discriminator would be the one which maximizes this objective, since we want to maximize the log likelihood of dx and maximize the log likelihood of 1 minus dgz. So for that, the optimal discriminator would be the one with which maximizes VGD. But the purpose of the generator is to fool the discriminator. So to be a good generator, this objective function should be minimized. So the GZ should be the one among many possible generators which minimizes this objective function of gain. So for that to achieve, we train the generator and discriminator together in parallel in a minimax game. So let's look at some theoretical properties of the gain objective. So theoretically, if we assume unlimited capacity for the generator and discriminator and unlimited training data, then the objective min G max D VGD is equivalent to Jensen-Shannon divergence between P data and P generator. And global optimum or Nash equilibrium is given by when P data is equal to P generator. So when these two distributions becomes equal, then we would achieve the optimal point for both generator and discriminator. And that is if at each step, if D is allowed to reach its optimum given G and G is updated to decrease VGD, then P gen will eventually converge to P data. That is, P data is fixed. That is, we already know because we are given an input. P generator depends on the produced images or the produced outputs, and by changing the parameters of the network, we can the outputs are changed and the P gen is changed. So once these two becomes equal, we would reach an optimal value, and P gen is changed such that VGD is decreased, but P data is changed such that VGD is increased. So these two would reach at an optimally trade-off level somewhere in the middle for VGD, and a convergence point would be achieved. So let's see how gain is trained. So for training gain, we can alternate between gradient extent on discriminator, since we want to increase the VGD for this discriminator. So we would use gradient extent. That is, the parameters of the network would be changed in the direction of increasing VGD, or in the direction of positive gradient in the direction of the gradient of VGD. While for the generator, since we want to decrease the VGD, so the parameters would be updated. The parameters of the network, the weights, the coefficients would be updated in the direction of in the negative direction of the gradient of VGD, or in the direction of decreasing VGD. So and since we can also write this min G VGD as EZP log 1 minus DGZ, replacing the value of that by this formulation. So in practice, we can do gradient extent on generator as well, or we can by maximizing log probability of discriminator being wrong. So replacing 1 minus DGZ by DGZ. So we can replace this min argument by max argument. So then in both cases, we are basically using gradient extent. Okay, so let's see some examples how gain is implemented. So the first example or the first architecture is called a non-saturating gain loss, which optimizes, which alternates between minimizing the log likelihood of 1 minus DGZ versus maximizing the log likelihood of DGZ. So here you can see the minus log DGZ, and the gradient is large at the beginning and small for the gradient is large for low quality samples and small for high quality samples. While for log of 1 minus DGZ, the gradient is large for there is a low discriminator score for low quality samples, and these samples already fool the discriminator, so we don't need large gradients here. And we want to learn from confidently rejected samples, but gradient here are small. Let's look at the training algorithm of NS gain. We update the discriminator and repeat it for k steps. So at each step we sample mini batch of noise samples Z1 to Zm, and mini batch of real samples X1 to Xm. Since the input to the generator would be noise samples and the input to this discriminator would be real samples. Then we update the parameters of D by stochastic gradient extent on this average of the VGD. Then we update the generator. We take the average because we are using a mini batch of size M, and update the generator by sampling mini batch of noise samples and update the parameters of G by stochastic gradient extent on 1 divided by M sum of log D GCM. And we repeat until we are happy with the results or until convergence is achieved. Remember, the difference between these two is that for the discriminator we use both noise samples as well as the real samples, but for the generator we only use noise samples, because generator at the input of the generator produces images from noise. Here is a conceptual picture of the gain. The discriminator on the input on the real data is pushed towards, so it becomes close to 1, and the discriminator on the fake data or on the generated images is pushed to make it closer to 0. So the generator is a black box to the discriminator. So here we have input which is noise, a generator which produces the fake image. Then we have a discriminator which can either receive real input or fake input, and then at the output we have the probability of the input to be as whether it's a real input or a fake input. So whichever among these two outputs is high, the detector would give that output as the classifier output. When we update the generator, we increase DGZ. We just increase DGZ. We don't there is nothing done to the discriminator. It requires backpropagation through the composed generator discriminator network. A discriminator cannot be a black box now. The generator is exposed to the real data only via the output of the discriminator and its gradient. So the generator only gets only gets random seed directly, and it get the real data only through the output of the discriminator because of backpropagation. Uh, when we use the GAIN architecture for testing, then the discriminator is discarded, since the main purpose of the GAIN architecture is now to produce fake images from random seed or from no input. So we only use the G part of the GAIN network or the discriminator generator network. That is, a random input is given and the output an output is produced, which is an adversarial image or adversarial input. Let's look at some results on the GAIN, original GAIN. We have MNIST digits. You can look at these images. These are all real inputs, and at the last column you see nearest real image for samples to the left. So to the left there is a 0, so there is a 0 produced here, 9 and 9 is produced here, from 2 2 is produced, and 8 is produced. Another example is Toronto face data set, where fake images are produced based on the inputs given to a generator discriminator network. Another formulation or another type of architecture of GAIN is called DC GAIN, which is an influential convolutional architecture for generator. So at the input we have uniformly distributed input Z. It is projected and reshaped and then passed through some convolutional layers till it produces an output which is of the dimensions of a real image. Tangent hyperbolic activation is used in the last layer. So this type of generator is called a DC GAIN. The discriminator architecture is empirically determined to give best training stability. We don't use pooling and only use strided convolutions. We use leaky ReLU activations, which produce sparse gradient because sparse gradient cause problems for training. And we use only one fully connected layer before the softmax output. We also use Bayes normalization after most layers in this discriminator as well as in the generator. Here are some results. All of these images are produced through DC GAIN. None of them are real images. They are generated bedrooms after one epoch. There's generated bedrooms after 5 epochs. There are more bedrooms. There are some interpolations between different points in the Z space. Let's look at the vector arithmetic in the Z space. So we have a smiling woman minus neutral woman plus a neutral man, which produces let's see what and we can also use DC GAIN to post transformation by adding a turn vector. So at the input we have these kinds of inputs where there are images of men and images with glasses and without glasses, and there are images of women without glasses, and these inputs are used to generate fake outputs where the purpose of generator image is to produce a turn in the pose. The problem with the GAIN training is stability, that the parameters can oscillate or diverge. Since we want the network to learn and to optimize between high VGD for the discriminator and low VGD for the generator, so sometimes it can oscillate or diverge, and the generator loss does not correlate with sample quality. and the behavior is very sensitive to hyperparameter selection as well. So hyperparameter selection is very critical in case of gain. Okay, I guess this is enough for gain right now. We will cover some more details about gains in the next lecture. If you have any questions, you can ask them through email or through chat. And that's all from my side now. Thank you very much.